So, continuing again on the root locus thing. So, we just left with a couple of rules. So, the first one was angle of departure from an open loop pole. Okay, why is this important to compute? So, in one of our earlier examples where we had a pole at origin and then we had something at j to omega minus j to omega. Okay, so one guy was going to infinity through the real line and then we had asymptotes this way and these guys were going like this, right, like this to infinity. This guy was going like this to infinity. So, who decides, right, of how this guy goes? Why doesn't it take a steeper angle and go like this, or why doesn't it go, wander here and then again come back and say, oh, this guy is here, no, not like this. So, we will say who decides, or what is there anything that will tell us which direction I should be moving, right? Okay. So, this is decided by something called the angle of departure, of which direction I should go. Okay. So, the angle of departure, the formula says is the following, right, the phi of p from an open loop pole. Let us say I am just looking at one pole under consideration, is again it should satisfy the angle criterion, right. So, all the time we are just looking at this one, that 1 plus k times g s times h of s is 0. So, all this criterion, all we do is just try to satisfy this criteria, right, nothing else, or just that the magnitude criterion and the angle criterion, as simple as that. Okay. So, the angle of departure is given by again this angle criterion. So, a little modification of that plus phi. Okay, what is phi? Say I am interested in some pole and this phi is the net angle contribution to this pole by all other open loop poles and zeros. Okay. Now, this is for pole, right, I go away from a pole and then I end up at a 0. So, I arrive at a 0. So, which direction do I arrive? Do I arrive along the axis or do I just do some circular behavior or whatever? How do I arrive? That is also important, right. So, the angle of arrival is again defined similarly. Okay. So, let us try to understand what this means and say draw a little picture here. So, let us say I have 6 poles and 1 0 and I am interested of how does P5 move. Okay. So, let us get a little scenario here. Okay, let's get rid of this. Okay. So, this is my plane and say, well, I have, let me call this P1, I have P2, P3, P4 and say I have say P5 and P6 be here. This P1, P2, P3, P4, P5 and P6. Okay. And then there is a 0, right. So, let us say that the 0 is sitting somewhere here. Okay. Now, I want to see which direction this guy should start moving. Should it start moving vertically downwards or somewhere here or somewhere here, okay, for any arbitrary scenario. And let us say I just take a point very close by here, this one, and I call that point as S0. Okay. Now, for this S0 to lie on the root locus, it must for sure satisfy the angle criterion. Okay. Now, and this so which this is just very close by, right. So, let us see, okay, so I just draw these angles, this will be theta 4, say theta 3, I have theta 2, I have theta 1 and the angle here would be this guy, right. So, some joining this line from here. So, that would be some theta 6 and then say angle of the 0, I will just call this theta. Okay. And then this guy is somewhere here, right. So, the angle here would be, so this guy is actually moving in this direction. Right? So, this is the angle of theta p, right, the pole which I am interested in. Okay. So, here there are phi's and thetas, but does not matter, right, you can just use whatever. Okay. So, for S0 to lie on the pole, so what should happen? That all the sum of all these angles should again be multiples of 180 degrees. So, what is the, how is the angle criterion look like? The angle of the 0 is just theta and then I have angle of all the poles, that is theta 1, theta 2, theta 3, theta 4, I have this little theta p, and theta 6 is again plus minus 180, and 2q plus 1 blah blah blah. Okay. Now, I am interested in this angle, right, this guy, this little angle, it will tell me where I will go, and therefore, I just substitute this, and this theta p or even phi p whatever is simply plus minus 2q plus 180 plus all the other remaining angles, they just go here, and I will just call this some theta prime, right. So, where this guy or this theta prime here, or okay, I will just call this phi just to be consistent with what is the notation over there for all the others, you can see. Okay. So, this phi is the net angle contribution to this pole by all other open loop poles and zeros, right. So, that is how I compute this theta p. Right. So, this is how it would look like. So, this phi is the angle of the zeros minus all the angle of the poles, and this is how I get it, right. It's kind of straightforward to look at it, right. And again, because S0 is very close to the departure point or the pole, this will be the departure point, and as S naught tends to the pole P5, well, that particular angle contribution will come 0, and then this, and then the other poles or the angle contribution by the other poles will satisfy the angle criterion, because I am not moving, I am just at that pole, and that is the limiting condition as S naught goes to S5. But S naught being very close to S5, how do I compute the angle? Well, that is just by this phi over here, this guy. Similarly, I could even do for a 0, right. It's exactly the same procedure what I would do for a 0. Take the 0 and you can just compute, take a point just to the left or right, or top or bottom of the 0, and then the angle could be computed kind of quite easily. Okay. So, we do an example. Sketch the root locus for a unity feedback system with open loop transfer function. Again, we have complex conjugate poles, open loop, this is 0 at -1, n equal to 2, m equal to 1, number of branches is 2, 1, and there is a 1 0. So, one pole will go to 0 and other will go to infinity. Okay. And the two branches originate from here when k equal to 0, and m equal to 1, one of the branches will go to this guy, another will go to infinity. Okay. So, let us see how the plot looks like. Right. Okay. So, I will just plot, this is a rough sketch of it before. So, okay, this is a good space here. So, I have a 0 at -1, and my poles are here, -2 plus J3 and -2 minus J3, a pole here and a pole here. So, I just want to see which direction this move, but before that, well, let me do the first rules, right. Which point is on the real axis? I know that when I start from k equal to 0, I am here, k equal to 0, I am here, k equal to 0, I am here. Now, just look at this, there is nothing here, right. So, this point would not, this region would not be on the root locus, right, there will be nothing here. Then look at the point here, right. So, from here I go to the left of -1, there is just 1 0, odd number. Then I go again here, there is again an odd number, 1 2 and 3. Sometimes we can even neglect this complex poles for counting, because they always are in conjugate pairs, right. So, there is even before this guy, there will always be an even after this guy. If there is an odd, there will be an odd. So, at least I know that the entire this guy is on the real axis now, is on the root locus, correct. Okay. I will not even draw the arrow at the moment, just to be a little safe. So, where is this guy? Oh, this entire line is on the root locus, starting from the left of -1. Okay. So, again I do all the basic computations that, well, there is one guy which goes to infinity. What is the angle which that guy goes to infinity? Well, that angle is 180 degrees. It is just very straightforward to compute. N minus m is 1. So, this phi will be 180. Well, and then these guys, well, do they really meet at some point and then go away? I can just find by dk by ds equal to 0. and the solutions would be, well, this one minus 4 and 2. And I don't really, I'm not really interested in this guy, right? This is on this point does not really lie on the root locus. I'm not ignoring this because it's an unstable region, right? I'm just ignoring because the root locus still tells me that I just cannot go here, right? Because I cannot be on any of this line because there are no poles or zeros to the right of this. Okay, so I'm looking at minus 4.16. So this is the real part here is minus 2, and say this point is minus 4.16. Okay. Okay. So I just go now to compute the angle of departure from this side and departure from this side, right? And then there's this formula phi of p, if I am looking at this guy, would be plus minus 180 plus the contribution of the other two guys, and if I am computing phi for this guy, it would be this phi would be the angle contribution of these other two guys. Okay, I can just compute. This is kind of very straightforward to check that phi for this guy would be 198 this way, and phi for this guy minus 2 minus j3 would be 165. Okay, so I just know that, okay, I am just from here, sorry, I just move in this direction. Here I just move in this direction. I also know where I am meeting, right, at minus 4.16. So the locus will start from here, will come here, will come here, and therefore the directions would be something like this. This guy moves here, this guy moves here, this guy goes here, and this guy goes here, right? So now I know why is it this way? Why is it not like something like this or any other thing? Why is it not like this, right? So this angle tells me how it behaves. Okay, so this is something not very surprising, this rule. How do I know if my root locus intersects with the imaginary axis? Well, when I hit the imaginary axis, say I have a root locus which is like this. Let's say I have 3 guys here, and I say, well, this guy is going, I'm just drawing an approximate plot, right? So this guy, there could be something like this, right? There could be possibilities of this thing, and these guys are going here. So these are all k equal to 0, k equal to 0, k equal to 0, and I see that after some values you are actually going this side, you are going in the unstable region. Now, can I really compute this value when it becomes unstable? There was another example where my poles were here, here and here, and then the root locus, well, one guy was moving this side and other 2 guys went here. So for any value of k greater than 0, it was always unstable, right? That was not difficult to compute. Now, how do I handle these conditions? Well, I know something called the Routh-Hurwitz criterion, right? The intersection of the root locus with the imaginary axis can easily be determined by the Routh criterion. Just to see how can, so we had done some problems where we were computing stability with respect to a parameter, right? If k was between this number and that number, the system is stable. If k is greater than this number, system is stable, and so on, right? Okay. So, and then the open loop gain k at any point on the root locus is just given by this. I think this we had even discussed in one of our very earlier slides. What given a point k, how do I find the given a point on the root locus, how do I find the gain k at that point? Well, it's just simply like this. There is nothing special here. Of course, now if you do an MATLAB, you just move the cursor, it will actually tell you the values. But where does that come from? That comes from something here. Okay, so just to do another example, so we have g of s is k, I have a pole at the origin and 2 other poles which are complex conjugate minus 4 plus j4 and another pole at the origin. So I start from here, so I have a pole at the origin and I have 2 poles here. This is minus 4 plus j4 minus 4 minus j4, and this is the origin in the sigma and j omega axis. Okay, so there are 3 branches, all of these things will go to infinity because there are no zeros. Okay, so which points of the real line lie on the root locus? Okay, so this is fairly obvious because at any point if I go to the left of 0, I look at the right, there will always be an odd number of poles, 1 until I reach here, and after that there will be 3. Okay. In the usual process of finding how the root locus or how the roots proceed to infinity, they will be at angles of asymptotes at 60, 180 and 300 with the standard formula, and then the centroid point of these asymptotes would be minus 2.66. So, somewhere over here. So, this is my sigma I. Okay. Okay, so the breakaway points, well, I just look at dk by ds equal to 0, I find k and then solve for dk by ds equal to 0, which gives me the breakaway roots at this point. And I could actually see from here that these points are very unlikely to be on the root locus, right. So, so look at this minus 8 plus minus j. So, I am somewhere here, right. Then what do my asymptotes suggest is that, well, I am at 60, 180 and 300. So, which is at an angles like over here, right. So, this is where, so it shows that I should actually be moving towards the asymptote. So, somewhere in this direction, right. So, there is no way that I could reach these points based on the location of the poles, the centroid point and the asymptotes. Okay. So, for sure that even though dk by ds equal to 0 gives me a solution, these points will not lie on the root locus. You could also test this by the angle and the magnitude criterion. Okay. Now, I am looking at the angle of departure at these guys. So, angle of departure would be computed by, so this angle and this angle. So, that should be straightforward to compute. So, this angle would be the angle at minus 4 plus j4 would be 45 and minus 4 as j4 would be plus 45. Okay. Now, since these are moving in this direction and the asymptotes are towards the right of the imaginary axis, there could be chances of these guys meeting the imaginary axis. So, let us see if that is true. Okay. So, I write down the characteristic equation and I have 1 plus k s s square plus 8 s plus 32 and I draw the route table. So, 1 32 8 k, this would be 8 minus 8 times 32 minus k by 8. Okay. So, what happens when, say, when does this guy go to 0? This guy will go to 0 when 256 by 8 minus k equal to 0, or for a value of gain k equal to 256, I have this entire row equal to 0. Okay. Now, let us see how the auxiliary equation looks like. So, I have 8 s square plus k equal to 0 or 8 s square plus 256 equal to 0, which gives me s equal to plus minus j square root of 32, and this is the value of omega where it will cross the imaginary axis. So, this will be at somewhere here square root of 32 in the positive direction, square root of 32 in the negative direction, right. So, this gives me a lot of information now that there are no breakaway points, the root locus will actually cross the imaginary axis and it will actually do it this way, right. So, the angle of departure was minus 45. So, it will initially tend to move this way and this is square root of 32 on the j axis and then it will just asymptote this way. Similarly, this guy has angle of departure of plus 45. So, it will move this direction and it will cross the imaginary axis at square root of minus of square root of 32 and I will just do this one, right. So, we saw few possibilities here, right, that there are no breakaway points even though dk by ds gives me a solution. Second is to explicitly compute the angle of departure, right, and also to see exactly where the root locus meets my imaginary axis, and this is where the route table was very useful for me, right. So, if I now want to have a problem where I say, well, what are the values of gain k for which a system is stable? I will say, well, for values of gain k between 0 and 256, my system is stable, and for all other values it might go to the unstable region. So, I have a bit better understanding now of the relative stability in terms of the gain k. Okay. So, So that's about it, and this guy is kind of straightforward. Right? We'll just keep on moving to the left until it reaches infinity. Right? Very straightforward route for this guy. So to summarize module 5, we have learned construction routes for the root locus techniques. We also knew now does the system go to instability, and next when we meet, we'll do lots of things on the frequency response of the system. Now we were interested in what happens when time goes from 0 to infinity or gain goes from 0 to infinity. We will see what happens with changing frequency, right. So that we will do in the next module. Thank you.